of course, if you are giving a function such as ln1 plus x, then of course I can do this, right? Because the theorem says that if you have a function you want to represent it as a sum of a series centered somewhere, then there's only one possible candidate, and that is the Taylor series. And Taylor series, its coefficients are those, right? That's what Taylor series is, with those coefficients. And therefore, if you patiently take derivative one at a time, then you can prepare those coefficients, assemble them together to get the Taylor series. But the message here is that since it tells you that if you want to express the function as a power series centered at A, here centered at 0, right? Then there's only one possibility, one series. That's a Taylor series. And therefore, if you take other routes, no matter which route you take, you manage to find something you are sure, some series you are sure that sums to this function f, then that series must be Taylor series. And therefore, the logic is, if I have this function, you have a much quicker way of getting a series, much quicker way of getting a series centered at 0, which I'm sure is sum to this one, then why would I use, derivative order by order, right? That's the idea that I want to get across. In other words, I might as well just use the first method because if I'm experienced enough, I know that this one, if you take derivatives, that one I know there's a R series, right? And then if I integrate back, then automatically get something according to the big theorem last semester. I'll automatically get a series, R series, that I'm sure converges to this one based on the big theorem last semester. Not last semester, last section, right? And then in this section, since Taylor series is the only series that can do the job, and I'm sure this series can do the job, so this guy must be the Taylor series. That's a logic. There's only one series that can do the job, no matter how you find it. So I managed to find it the first way. I managed to find this much more quickly. And then since this is a series that can do the job, and I only know that there's only one series that can do the job, this guy, which does the job, must be the Taylor series. And this is just a confirmation of that. All right? Okay. And so these two we actually learned last section. These three are new. And here comes the next one. Next one is a big deal. Next one is called the Binomial Series. Binomial Series. And that is the last down the list. That is 1 plus k, 1 plus x raised to the kth power. Let me ask you some side question. What is 1 plus x to the first power? That 1 plus x? Right? What is 1 plus x to the second power? 1 plus 2x plus x squared. Right? What is 1 plus x to the third power? Anybody? 1 plus 3x plus 3x squared plus x third power. If I keep asking 1 plus x to the fourth power, I have to wait longer, I suppose. So what is?
1 plus 4x.
4x.
Plus 4x.
6x squared plus 4 x third power plus x fourth power. If I ask one more. Anyone?
1 plus 5x.
What's going on, Have you seen this before? I'm sure you have seen this before, Many of you you have seen this before, but far fewer of you have seen this and that. May I erase this?
Yeah.
So if this power, this k, is an integer, then you have these results. All right? And these results, if you look at the coefficients, 1 plus x is 1 plus 1x. 1 plus 2x plus x squared. 1, 2, 1. Next one, 1, 3, 3, 1. 1, 3, 3, 1. Next one, 1, 4, 6, 4, 1. Next one, 1, 5, 10, 10, 5, 1. You see a pattern here. In one row to the next, all you have to do is to start from 0 and end with, start from 1 and end with 1. This 4 comes from the sum of these two. This 3 comes from sum of these two. 4 comes from these two. And then, therefore, if you go to the next row, start with 1 again. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And you see that in each row is perfect symmetry. And therefore, you can predict the next one, which is 1, 6, 15, 20, 15, 6, 1. Always start with 1, end with 1, right? And which means that 1 plus x, 6 power is 1 plus 6x plus 15, x squared plus 20, x third power plus 15, x fourth power plus 6, x fifth power plus x sixth power. This is called binomial expansion. So this is called binomial expansion, almost. And then here is a generalization of that. As it turns out, this exponent, this power, if it is not an integer, then there is still a result. And this result looks like this. If you use the notation in the book, there is this notation. It's let me write like this. Here's the notation: 1 plus x to the k's power here, okay, is equal to the summation. N goes from the lowest power, which is 0's power, to the highest power, which is k's power, right? And then each term is x to the k, and that coefficient is called, each x is x to the n. N goes from 0 to k. And the coefficient of x to the n is called kn. And if you have taken statistics, sometimes it's called this. In your graphing calculator here, most of the graphing calculator probably will write it as, I don't even remember, is that written this way or that way? Anyway, it's, and I'll not be surprised if many of you probably have seen this before, and if you didn't grow up here, perhaps you have a similar notation and it's upside down. So it's very confusing. You go from one book to another, from one country to another. This thing it's written differently, so you have to be careful. What someone calls C63, probably someone else would call C36. So a different notation convention, extremely confusing, right? So in this book, it right this way. right? It's written that way. Okay, anyway, it's just a notation, all right? And there's some combinatorial meaning to it. And combinatorics is the art of counting without really counting. And so these are combinatorial factors in these cases. For example, this 10, for example. This 10 has to do with you have 5 balls in a box, and you want to go in and grab a handful of 2. I don't care about ordering. For example, the balls are number 1, 2, 3, 4, 5. Then grab a handful of 2. It could be number 3, number 5. You know, the ordering doesn't count, right? And how many handful of 2 are there possible? 10. Right, that sort of thing. So there's some combinatorial significance to these numbers. But here, we generalize it. To generalize it, it's like this. You can guess what it's like. If you look at this one here, and then you erase this, and closely look at one example. This guy. 1 plus x to the 6th power. And I closely examine each of the 7 terms. The first one is 1. The second one is x term is 6x. This 6 obviously comes from the 6. Alright? And the next one is what? 15x squared. Where does 15 come from? It turns out it's this. 6 times 5 over 2 factorial. X squared. Next term is x cubed, which is what? 20. 20 turns out to be this. 6 times 5 times 4. You count down, and then divide it by 3 factorial. Count up 1, 2, 3. The x third power. Next one is 4th power. 4th power, x 4th power. Coefficients is 15. 15 turns out to be, of course, I have seen 15 before. This one is 15, right? But it also can be written, if this trend persists, the next one you can guess. What is that? 6 times 5 times 4, what am I going to write? Times 3. And then 1 times 2 times 3 times 4. Which turns out to be the case. You see that 3, 4 cancel out, 2 cancel this, 3 times 5, 15 indeed. What's the next one? 5th power, 6, right? 6, I have seen 6 before. 6 is this one, right? But there's another way of writing it, and now you can guess. 6 times 5 times 4 times 3, what? Times 2. And then this is 1, 2, 3, 4, 5. And then, 5, 4 cancel 5, 4, 2, 3 cancel 2, 3, you're left with 6 indeed. Right? So this is x to the 5th power. And last one is x to the 6th power. And guess what? The trend persists. 6, 5, 4, 3, 2, 1. 1, 2, 3, 4, 5, 6. Is that right? Now, if you were to naively follow this trend, then there will be the next term. And what do you think the next term should look like? Wouldn't that be, well, you see that every time you have one extra factor,
0.
Is that right? So you have 6, 5, 4, 3, 2, 1, what? 0. Over 1, 2, 3, 4, 5, 6. 7, right? 0. You see that? You hit 0. Mm-hmm. And then, so it terminates. Okay? And the formula, more general formula that we present, which works even when k is not an integer, well, in general allows you to proceed. There's no 0. It doesn't stop at finite number of terms. It's go on forever. And that formula is this. 1 plus kx, just like those 6x, right? Plus next one is k times what? K minus 1, 1 times 2, x squared. Yeah. Next one is same pattern. K, count down, k minus 1. Count down again, k minus 2. Right? And down here, 1, 2, 3. 3 factorial. X third power. And then plus, next one. I think I can erase that one. Next one is k, count down, k minus 1, k minus 2, one more, k minus 3. And downstairs, 1, 2, 3, 4. And then x to the fourth power. Etc., etc., etc. Example. One plus x square root. And I want to find a power series, a Maclaurin series of this, which is to say that I want to find a Taylor series centered at 0. And this one turns out to be that pattern. This is 1 plus x to what power? 1/2 power. All right, so k is 1/2. And according to this binomial series, this is new in this section. It is 1 plus kx. K is 1/2.